All right, guys, can you hear me again? Can you guys hear me? Yep, sure, can you hear me? That's great. Okay, so we have these proposed we have these proposed approximations to the derivative. Let's try to study and see what kind of convergence properties they have. And so let's look at the forward. Actually, this is the one we take the derivative and you use. This is the one that takes u of x plus h. Remember, h here is now positive. Here, h is positive. We want to see how good a job this guy does. So we want to compare. We want to compare this forward approximation. Compare this with the actual derivative, and see how is this difference. Okay, so let u be smooth, and apply Taylor. So we apply Taylor's theorem. So if I want to compute or approximate the value that u has at that later point, right, we want to do that because this is what we have up here. We can write this out here in a Taylor expansion. Write this out here in a Taylor expansion. This will be u of x plus, and then the distance between x and x plus h. This is h, and then the first derivative plus, and then 1/2 h squared, and then the double derivative plus, and then something in big O of h3. You have a smooth function. Taylor's theorem says that you can write, you can expand this thing out, and you'll have a reminder, an error term that is in big O. Right? This one here is big O. So now I can compare the two. I take the difference, and let's see how bad it gets. Then I'll have d plus the derivative in x minus the actual derivative, and we'll just plug in what it is. So we have over here, the definition will give me 1 over h. I have this guy, u of x plus h minus u of x minus the derivative. So the first order of business is I want to put this 1 over h outside. Okay, so I can do that. 1 over h, u of h plus x minus u of x, and then I need to get this one outside. I have to multiply here by an h. Right, so nothing happened here. I just moved this term inside the bracket, and to do that, I need to multiply by h here because I'm dividing by h out here. And then I use the Taylor series. So I have this term here. I have minus ux here, minus hu prime here. Okay, so what is left is these two terms. I'll have here minus, I'll have here 1 over h. Then I'll have 1/2 h squared u double prime of x plus big O of h to the power 3. Okay, so I can simplify out now. This will be 1/2, and then it will be h u double prime of x And I'll do the same thing here. This will be O of h squared. And so you can see the lowest order term, we're thinking about h being small here, right? So this is as h goes to 0. Excuse me. This here will be O, big O of h. Right? This here is as h goes down to 0, right? H is positive. Where is it? It's positive, and it goes down to 0. The leading order term here would be h. Right? Had we, yeah. So that shows us that this is one will say that this is a first order method. This is a first order method. First order. And that's because there is a 1 here. This is h to the power 1. And this was the forward. And we'll say that because of this calculation, we'll say that this is a first order. So the backward. The backward, this is try yourself. And you should get exactly the same. So what I want to show you is the center. Right, so we recall what the center is about. Recall that the center was dc dcx of u of x. This was defined to be u of x plus h minus u of x minus h divided by 2h. And again, h here is positive. How does this guy work? Well, we're gonna do Taylor twice. So we're gonna use Taylor twice. We're going to expand these two out. So I'll get, as before, the first one. This is just u of x plus what will be h u prime of x. Then 1/2 h squared u double prime of x plus big O of h to the power 3. And then I will do the one with the minus. So the only difference is going to be, I need to put a minus sign here. This is h squared, so whether I have h or minus h squared, that's the same. And this one here is just O. So it's basically the same as I have. The only difference is I'll get a minus there. Right, so this is the difference we want to note. This is the thing to note. So note the difference. Note the different signs. So now we can compare the center approximation with the actual derivative. So we look at dc x u of x minus u prime of x and see how big that guy gets. Okay, so it's like before. This is 1/2h u of x minus u of x minus h. And then you need the derivative. And as before, what we want to do is we want to move this derivative inside the parentheses. We want to move this u prime inside the parentheses, and we can do that by multiplying onto 2h. So this is 1/2h u of x plus h minus u of x minus h minus 2h u prime of x. And so comes the time where we want to insert what these two here are. We want to insert what these two here are. 1/2h. And so what do I have here? This will be u of x plus h u prime of x plus 1/2 h squared u double prime, and then O of h to the power 3. Okay, that was the first one. And then comes a minus u of x. And then there's a minus, so this is a plus h u prime of x. Comes a minus. Comes a minus 1/2 h squared u double prime of x. And then I have my O of h3. I already got that. And the last part is this one, minus 2h u prime of x. And so what we see is a bunch of things will cancel out. Like these two guys cancel, these two and that guy will cancel, and these two here will cancel. And all I'm left with is 1/2h O of h cubed. So this is O of the constants don't matter. This is O of h squared. So this is a second order method. This is a second order. Get a square here, whereas over here we only got the power 1. We got a first order. This one here is a second order. And h squares, this one goes much faster to 0 than h. And so this converges. This is a smaller error than you make. A smaller error. Right, because h squared goes to 0 much faster than h goes to 0. That's what we had on one of the examples before the break. Any questions on this part? I do apologize for all the noise. They are working hard outside my window. So if you hear this buzzing sound, this is the construction workers working out there. Are there any questions on this this convergence? But to let me just remind you again what the goal here is. Like we're looking at speed and accuracy, right? So now we're talking about the speed here. Accuracy, this is something that we're going to be addressing probably next time. Turns out, like based upon this, you might want to use this thing here. It turns out that while it has a higher order, it's not stable at all. So yeah, we might talk about that next time. But for now, we're just trying to get a feeling of for like how big errors do you make when you use these different approximations. And so for us, it's not. We will have a second order. For us, it's not enough just to have the first derivative. We'll also need the second derivative. We'll also need the second derivative. So we'll need the second derivative. I mean, after all, we're going to be looking at the heat equation. We'll be looking at the heat equation, right? That's the one that says something along the lines that ut is equal to 1/2 uxx, right? And there's a second derivative here. So we're going to be needing a second derivative. Okay, so so the second derivative we had. So while we had 3 suggestions for approximating u prime of x, we only have one. We only have one suggestion. for the double derivative. And this suggestion is as follows. This is a d, and then you put a 2 up here. That's because it's the second derivative. The second derivative approximation, the way that it's suggested to approximate that is u of x plus h minus 2, and then you get u of x plus u of x minus h. Everything divided by h squared. This is how it's suggested to approximate this guy. And there's a little, so the claim is, we'll look at how it approximates the second derivative. This is actually going to be 1/12. You can see this is a higher order term in the Taylor approximation, and then you need a bunch of derivatives here. I think you need 4, 1, 2, 3, 4 of x h squared of O of h to the power 4. And the proof, I'm not going to write all the details because it's quite similar to what you've seen before, but you do an expand using Taylor. You're going to expand two things. You're going to expand this guy, and you're going to expand this guy into fourth order Taylor. Fourth order Taylor expansions. The fourth order Taylor expansion. And then you're gonna get this difference here. And so you can see the lowest order here. This is the second order. It's h squared. And this is the second order. Okay, so at this point we have talked a bit about how to approximate these derivatives. I want to get back and talk about how to apply this to the ODEs that we started out with, and then look at some code here towards the end. So if we look at the explicit Euler, so the explicit Euler, he says if I want to take a function, so I'm going to write the functions here again as f. I'll use the forward. So this here, I have this choice inside my function f. I can either put f at Tn or Tn plus 1. And if I put Tn, I'm going to get the explicit one. Right, so this is my approximation. I want to approximate the derivative. Okay. So this gives me the approximation. When I write Tn inside the parentheses, this is the function evaluated there. So now the approximation is going to look like f over here n plus 1. This is defined to be f of n. Right, so I multiply over, I move f over on the other side, I get an h, and then here this will be f at the previous point, fn, Tn. And we'll start out at that point A. Right? This here is going to be my Euler approximation to the actual solution of what I have up here. So I'm going to look at, let's look at some code. Let's look at some code to approximate f prime of t. I think my code is just going to say this is f of t. So so this is the exponential function. And the other one we could try to look at is f prime of t could be, I think I have a 1 here in my code. So I have 1 plus f of t, and then plus minus f of t squared, and then f of 0 is just equal to 1. And let's use the explicit Euler scheme to, so this right, this is the affine, and this one here is the Riccati. Let's try to apply the explicit Euler scheme to study the two of these, and let's just look at what the code does. This is my code. If I want to do the affine case, this is this one. I have 1 plus f here, and the initial point, this is my f0. My initial point is just equal to 1, and then I have the explicit and the implicit. Okay, so we're just looking at the explicit for now. So the explicit one, it moves through the time steps. I have my time horizon is 10 years or 10 units of time. I go from time 0 and then up to time 10 years. And then what I do is I take the Euler scheme. It says you take the function, you evaluate it at the previous point, and then time the time step. And if I do that, I'll get a sequence of points, and it will give me it's just Lec9. It'll give me, in this case, it'll give me an approximation to the exponential function. Right, the exponential function gets pretty big out near 10, so maybe we should look at it on a shorter horizon. Maybe we just do 2 here. And here we see the approximation. I took the interval from 0 to 2, and I divided it into 10,000 time steps, and I did this approximation. So that looks good. If we then move into more complicated equations like the one with the Euler scheme, so I'm now subtracting away. I'm subtracting away the square. So keep in mind, right? It starts at something positive. Starts at something positive. This here is the derivative. So if f ever gets to be 0, the derivative is positive. So if it ever gets down to 0, it's going to bump back up. And when it gets to be too big, f squared here is going to dominate. That means that the derivative is going to be negative. So this here should be the stable guy. If it ever gets to be too big, the square term will drive it back down towards 0. So let's look at the solution here. And you can indeed see this picture. If you were to compare the two solutions, we can do that as well. Wanted to compare, so I'll run it again. This here was the square, and then if I want to run the linear case, we can keep it on the same picture. So the red one, this is the exponential function. The blue one, this is my Riccati solution. The Riccati solution with a negative sign on the square term. And what I wanted to show you is what happens if if I put in, instead of a minus sign here, if I end up with a plus. Right, so now there's no penalty. When f gets to be big, f squared gets to be huge, and that means that the derivative is going to be huge. So here, this could be trouble. And you can see indeed that if you look up at the y-axis, the number out here, 10 to the 271, this is humongous, and you see the solution degenerates. Like, so it does exist up to some window of time, and maybe if I lowered the length of interval I'm looking at, maybe I can get a nice solution. Doesn't seem like it. Try again. Doesn't seem like it. Let me lower even more. Yeah, so here it does exist, but at some point it blows up. So if you look at it from 0 to 0.1, this is going to work, but at some point that derivative gets to explode simply because f explodes. So there are lots of ODEs that don't have solutions on the entire interval. And so when you write your code, one needs to be aware that you're studying an equation that only has a solution up to some given point. You might have this explosive behavior. Here, I don't know when the explosion when this explosion happens, and we can experiment with it. So this still looks good. This is up to a half. And how far out you can go before it explodes. Yeah, that's too much. So 0.9, this is already 0.9, this is already too much. So maybe it's 0.8. It's also too much. 0.75 works. Maybe that's as far as it can go. No. Okay, so it explodes out there at some point. I think a half was okay. Yeah, a half is okay, but when you get out past a half and before 0.75, the thing explodes. This was the explicit Euler. We can also do the implicit Euler, which is related to the backward discretization that we just talked about. So let's try to do him. Get back on the slides. So this was the explicit one. So now let's do the implicit one. Do the implicit Euler. So it's roughly the same as what you have here, but not quite. So you approximate the derivative. You would approximate the derivative with here you would approximate it with the right endpoint, so tn plus 1 and tn plus 1. So this would give us the approximation. This would give us the approximation if n plus 1 is equal to fn plus h times f. So this is the definition. This is how we get the next one in terms of the previous one. And here you have f at n plus 1, tn plus 1. And you have f0 is equal to a. All right, so this here is implicit. This is an equation you need to solve. This needs to be solved. Because you've given the previous one, but then you have to solve this equation here for fn plus 1. And maybe we should just look at an example, the one we just had on the code, on how one would go about implementing this. So let me turn this thing off here again. So in Mathematica, to do the implicit one, I have to solve this equation. So I'm given the previous one plus f, but now the g that I have in here, this is the thing that also has to appear on the left-hand side. So I've got to be able to solve this equation. And if I can, this is going to give me my approximation at the next time step. So I'm going to plot both the explicit and the implicit one, my time horizon, let me turn it back up to say 10 years. Oh gosh, and now of course I forgot to. Which one is it? Oh, I turn this thing off here. Aha! What these ones? Oh gosh, how do I get this thing to stop? How do we get this thing to stop? How far along are we? We're almost there. We'll just hold up a little bit and let it count up to 1,000. Oh, it's 10,000. We don't have all day to do this. There you go. Let's try this one more time. I should have put a comment here. Yeah, this one. Okay, let's try this again. Now this is quite a bit slower, and this is because I have to solve the equation. It should not take this long though. Oh man, it's taking forever. Let's try this again. So now this won't do anything. All I wanted to show you guys was the difference between the implicit and the explicit Euler scheme in a simple example, and Mathematica doesn't want to play around. So let me make the position less. And there we go. Okay, so less precise. So you can see that the two things are not exactly the same, but they're pretty close. But there's much more. There's more work to be done here in terms of implementing this scheme, because you have to solve this equation every time we move back. So it begs the question, like, so what do you gain from doing this? What do you gain from what kind of benefits do you have by doing this extra work? And so we should compute these the corresponding orders of convergence. So let me try to take you through this in the last part of today's lecture. So let's look at orders, convergence orders. So order of convergence. So the so say that at time Tn you're accurate. So this is the same as Fn. So this is a local analysis. And so what we're interested in is how good is the next approximation. So what we want to do is we want to compare the actual solution with the approximation. we do Taylor again. Actually, we write out the actual solutions Taylor expansion. So here we expand. We expand f of Tn plus 1 as f of Tn plus, and then is the time step, which is h, times f prime, and then plus O of h squared as before. So we expand that out here. We're going to get the absolute value. What we have would be f Tn plus h f prime at Tn plus the arrow term minus the the approximation. So if we use the explicit, here, this is going to be minus Fn minus h, and then you have your f of Fn Tn. Right, this was the explicit. So we expand this, and the other one we use is that Fn plus 1, this was Fn plus hf, and then the explicit one says that you take the previous one and plug it into the capital F function. Okay, so how bad can this one here get? Well, we're doing this local analysis, so that point and that one, they are the same. And furthermore, these two here are the same because we are saying that these two here are the same. So all in all, what we end up with, is, I should write that out. So this difference, how bad a mistake are we making, how big an error are we making, this is going to be, actually, most of them will cancel out. We'll be left here with O of h squared. This was local, so locally when f of Tn is equal to f of n, we'll have this, and so globally, you'll have to add them up. You go down one. Globally, you'll have O of h. So this is first order. So every time you move one out, you're going to make this mistake. Okay, so how many times have you moved out? Well, then you'll go one down here because you have to add them all up. This was the convergence for the explicit Euler. This here was explicit Euler. Explicit Euler. We want to do the same thing for the implicit Euler. So to do it for the implicit Euler, let's make the, so now we want to move into the implicit one. The implicit Euler. So here we need to make an assumption that says consider f Lipschitz. What does it mean to be Lipschitz? It means that if I take f evaluated at 2 points, t and f, and I subtract away it evaluated at 2 other points, s and t, then this is going to be less than, there's some constant here, c lip, and then there's the difference between f and g. For some constant, there exists a constant c lip such that this derivative, it doesn't behave too crazy, and this is for all f and d. So this is the Lipschitz property here. And then, given that, we can now move on and do the same analysis as what we had before. So if you do so as before, say that we accurate at time tn. So make that that assumption and then expand as before. And let's look at the difference between the next ones, tn plus 1 minus f of n plus 1. And now we're using the implicit Euler scheme, right? That's the one we're working on. So what are we going to get this time? Well, first we expand in the Taylor approximation, just like here. We'll do the same thing again. Do the same thing again. If I wanted to write, so what will it be this time? I would have f of tn plus h f prime. I want to get something here with tn plus 1. How do I need a different Taylor approximation. So if I were to do f at tn, I will get this as f of tn plus 1. Then I'll have to have a minus this time of h of f prime of tn plus 1. Plus O of h squared. And so what would I get this time? I need f tn plus 1 to be, what is it equal to? It's equal to f of tn plus h f prime of tn plus 1 plus O of h. I don't have to change the sign here, this doesn't matter. So this is the thing I need to plug in here. So I want to express this one in terms of its Taylor approximation. Okay, so I can do that. This is tn plus 1 plus my error. And then I need the Euler. This time I'm going to use the implicit Euler. So there will be a minus. And then the implicit Euler will say this is f of n minus hf. And now I have to evaluate here at f at n plus 1. tn plus 1. So that was a big difference between what we did before and what we do now. Before we just had n here, now we have n plus 1. Okay, so we need to simplify, and as before, we will simplify using what we had here, but what about over there? So this here becomes the f at tn and the fn. By assumption, you're the same. So here I'll have a difference. You'll have a difference f prime at tn. And then you have this capital F at the approximation. So we will end up with an h times, and then I'll have f evaluated at f at tn plus 1, like that was this guy. This here was my f prime. Tn plus 1 minus, and the h is outside. So here we have f at fn plus 1, Tn plus 1. And the correction term is inside. This is O of h squared. And now comes the time where I'm using the Lipschitz property. I'm using the Lipschitz property. This here is bounded by h, and then I need the Lipschitz constant. And then it's just going to be the difference. It's just going to be the difference between the two entry points. So f at Tn plus 1 minus f, the approximation, fn plus 1. And I need the, so h is out there. So if I want to eliminate the h, I'll have O of h to the power 3. This is not right. This is, this is wrong. This thing here, there's no h out there. This is just O of h to the power 2. The absolute value should be there. And this should be 2. Okay, so combine now the two sides. I will have what will I have? I'll have, if I combine, I have the same term on the right hand side as I have on the left hand side. I'll get here that the absolute value of ftn plus 1 minus fn plus 1, the approximation, this will be bounded by, I move this to the other side and divide over 1 minus h, and then the Lipschitz coefficient times O of h squared. Which is, this is the same as what we did in the other one, the explicit Euler scheme. Wherever it went. Page 26. We had the local analysis was O of h squared. I think here is O of h squared. Right, so globally, you lose one of these, and you're going to get O of h. Right, so there's no difference. You have the same order of convergence. So why ever use the implicit method? Well, it turns out that there are very good reasons to use the implicit scheme. This is about stability. Stability. This is going to be next. This is going to be next time. Because you have the same order of convergence. The both first order schemes, both first order approximations. One has a lot more work involved, and it didn't lead to higher order, right? This thing here, it doesn't cancel out. You have this 1 minus, right? So when h is teeny tiny, this is basically 1. So you're just going to get O of h squared, big O of h squared, and then locally, that's locally, and then globally you go down 1 because you have to add them up to get up to. If you make the local error, then you have to get the global one. You have to add them up, and we go 1 down. Are there questions on the order of convergence? I think this is a good place for us to stop, and then next time we can continue. There's one more scheme. We have talked about the implicit and the explicit. There's one more scheme which is called the Crank-Nicholson method, and I want to talk about that next time. Are there any questions here before we hang up? Any questions before we hang up? Otherwise, we have office hours with the TA both tonight and tomorrow, and I have office hours tomorrow morning at 9 o'clock. So if you have any questions related to homework or about the lectures, you can ask them now, or you can ask them tomorrow. Okay, I wish everybody the very best, and I hope to see you either tomorrow or I'll see you again next week.